name is Ibrahim A. My friend is
Shukri Ibrahim.
Our project title is Performance of Concrete Using Bokola Soil as Partial Replacement of Cement. Introduction, this a local soil found in the north town of Mandera County. The existing scenario is that some buildings, like the one on the right, were built using this soil as a binder. People also use it for plastering. This soil is naturally available, so we think it will reduce the cost of construction, leading to economic development, hence raise the standard of living. Problem statement. Some of the problems include the production and exploitation cost of cementitious material due to the poor road and the cost. In Mandera, it is twice that of Nairobi. Depletion of natural resources due to excessive use of cementitious material. This increased carbon footprint, and then because people are already using it, there is a lack of specification and standardization for local material. So we needed to have done proper test. Problem justification.
In order to provide adequate and affordable, decent housing to meet the goals of the Big Four agenda and racial identity and the rest, we needed an alternative material to cement, which leads to production of lots of carbon. Hence, since usage of concrete around the world is only second to water, an alternative material like bokola will create will be to increase devolution also needs local solution. Bokola is used to some extent, hence the need for proper tests. Our main objective is to investigate the performance of concrete using bokola as partial replacement of cement. Specific objectives: one is to determine the physical and chemical properties of bokola soil. Two, to determine the properties of fresh and hardened concrete in which bokola is used as part of binder. Three is to determine the properties of mortar in which bokola is used as binder. Our research question, the first one is on strength. Does the concrete made of bokola attain the required strength within the 28 days? And to what extent bokola can be used in place of cement in making of concrete? And economically, does the use of bokola make housing and infrastructure more affordable? Our limitation, number one, is on chemical analysis. We have not stressed much on the chemical analysis of bokola. We only tested for basic oxides, and then the class of concrete is only limited to class 20 because of the new material, and the number of representative samples is only minimized to from 0 to 20%.
Reviews that are relevant to this include someone did calcite, termite, hill, clay powder, partial replacement. They realized the composition includes silicon oxide, aluminum oxide, and iron oxide. They tested for normal consistency and setting time from 0 to 40%, and they realized both initial and final setting time reduced. Someone else, Abubakar, did the structural and mechanical properties of termite soil after 28 days and realized the compressive strength was reduced. Lime was also done as partial replacement of cement by these guys. They replaced from 0 to 35% in concrete and 0 to 100% in mortar. The strength increased up to 15%, after which it kept on decreasing. Zollite and turf as partial replacement of cement were also done. They researched and they also realized from 5, 10, and 15% of fine aggregates, and they realized that 15% it was successful, after which it wasn't. Research gap, some pozzolanic materials like gypsum and lime have been studied quite a lot. We realize these materials are found around the world and in some areas of good economy and academics, hence get enough attention from researchers. Bokola material is generally not known to many and is found in predominantly dry, remote region with little attention from researchers for local solution from us. Methodology, this is our roadmap. We started by collecting the sample and we did a chemical analysis for basic oxides, after which we went to properties of bokola. Here we did specific gravity, fininess, consistency, and setting time. Then we did on mortar, and then we did on fresh concrete. The one we did our workability, especially slam test. Then on hardened concrete, we did compressive strength, tensile, density, and water absorption. And of course, at the end, we did analysis and comparison. Now, on to results, data analysis and discussion. The chemical composition of this bokola soil was analyzed using XRF test. We realized that it contained a very large amount of sulfur, 43.8%, against cement of 1.9%. And this high amount of sulfur, unusual in cement, could be from calcium sulfate, making this material more close to gypsum than cement really. It contains a good amount of calcium oxide, 35 against cement 42, silica 15 against 40, and these two materials are these two compounds are very important in cement because they bring the binding effect, and the silicon and aluminum produce firm and hard mass, hence the strength development. Properties of bokola soil, we did the standard consistency, realized that bokola required 227 milliliters of water to be consistent against the same amount of cement for 120. This means bokola needs more water than cement and small plastic. Setting time, the initial set for cement is 150 minutes, bokola is 307. Final setting for cement 295. The other one is 582 minutes. Although both realized the requirement of ACTM of requiring not less than 45 minutes and not more than 10 hours, we realized bokola needed more time to settle, and this is because of less calcium oxide and less silica. This means less hydration and less reactants. Workability.
The workability of concrete in which we use bokola reduces. The slumps were true, but the reduction may be due to consistency of bokola, which needs more water to be consistent. Compressive strength. The compressive strength of mortar also increased with time, but reduced with increase in bokola content. Bokola is weaker than cement due to less calcium oxide, silica, and it is also less finer. The compressive strength of concrete also reduced with increase with bokola contents, but increased with time. Increased with age, lower than that, but it is lower than that of control at all replacement. Those of 5 and 10% replacement satisfied the strength of class 20, and this shows the bokola soil is weaker. The tensile strength also increased with time, that is 7, 14, and 28 days, but decreased with increase in content. The tensile strength also satisfied the 10% of compressive strength for all the replacement. The concrete water absorption also increased with increase in bokola soil. This is due to
1 minute remaining.
Due to fineness of bokola, which is less fine than cement, hence creating porous spaces.
On to conclusion or recommendation, we concluded based on objective number 1, we realized that bokola soil contains elements of cement and it could show comparable properties. This includes setting time, fininess, all of which we showed the values. Bokola mortar also had compressive strength reaching up to 17 kilonewton per square meter, which is generally good. The use of this material can make housing more affordable, especially in large projects. Compressive strength in which this material we use as founder is okay up to and including 10%. On to recommendation, based on this study, we can recommend the cement replacement for this material up to 10%. We also recommend it to be used as binder and filler because of the bonding effect that it has. Since people are already using it for plastering, we think it's okay to continue, but to use bokola material as a retarding admixture because this soil is found in areas of high temperature, so we need to use it as retarding admixture to slow that setting of cement due to high temperature. We also recommend a future study for use of structural element.
Okay. Thank you for your presentation. Your time is up.
Thank you.
Let's get the comment from the panel members. There was a comment by Engineer Kyoko, or it was an observation. The presentation was dominated by one person. So I hope you rectified that towards the end.
I have one observation.
Yes.
I can comment they have quality presentation slides. Yeah, their presentation is good.
Thank you, sir.
Yes.
My name is Kiptoo and she's Ongeri, and our project title is The Comparison That's Made of Concrete Hollow Pots. The background study: in order to reduce the dead load in the rib slab, use of lightweight material in construction is necessary. At the concrete hollow pots and the EPS, as shown below, here is an example of an EPS floor slab, and to your left, you can see an exact slab. Now, problem statement: due to the increase in dead load of using concrete hollow pots in the rib slab, it's leading in the load-bearing element sizes, which may lead to the increased cost of the overall building. In order to curb this problem, use of lightweight, hence reducing the sizes of the load-bearing elements and the amount of concrete and reinforcement required. For our objectives, the main objective is the consistency of EPS and that made of concrete hollow pots. Our first specific objective was to determine the various concrete material properties indices. The second one is to design a rib slab made of EPS and that made of concrete hollow pots using the BS 8110 Part 1, 1997, set of concrete reinforcement and filler material in the EPS and the concrete of hollow pots, and do their cost analysis, do a structural design and cost comparison of the mentioned rib slabs. The limitations encountered is only one size concrete hollow pot were factored in, and only one slab thickness and class concrete 25 was used, and the cost of labor and transport were not covered. The previous research done, the compressive strength and insulation properties of both the materials, the EPS and concrete hollow pots, have been previously with more and stone was done by Githuku, and it shows that EPS had a higher cost than the stone and mortar. The crack patterns between and EPS availability and usage in Kenya was also done by Gugi in 2017, where that and it shows that because of its availability, it's not readily available. For the research gauge, however, there is no study on comparison between the EPS and the concrete hollow pots. For the research methodology, we did the sieve analysis, the specific gravity, the flakiness index, the strength of class 25 cement to be 27.65.
Our design of rib slabs, we did for the rib slab with EPS and concrete hollow pots, and shear force, and the reinforcement provided for EPS was 1T16 top and 1T10 plus and 1T12 bottom, 3T10 top and 2T12 bottom. And the results, we used concrete had a density of 15 kg per cubic meter, and the hollow pot had a mass of 17.6. For the reinforcement, by 19.15, and the cost of EPS was lower by 8.4%. And the volume of concrete in EPS was 0.3%, and the cost of EPS in slab was less by 15.7% as compared to that of total cost of EPS was higher by 62.8%. And in conclusion, the properties were satisfactory. Rib slabs design was also successful using the BSs. The overall cost of using EPS was 112,000, while that of using hollow pot was 87,000. And due to the high cost of EPS panels, the cost of slab construction will be higher. We recommend that the building using EPS and concrete hollow pots as filler material for slab is recommended to know the overall loading and cost of each in calculation of the total in order to know the precise total cost. Thank you.
Thank you for your presentation. Thank you for keeping time. Welcome questions from the panel members. Yes, Engineer Juki.
Please always take out the labor cost, because this is the biggest advantage of the save quite a bit on the labor. The biggest.
Do you get that comment?
No, we
We
didn't.
didn't get the
Marimu is saying that always when you're doing this comparison, always take into consideration the labor cost, because that's where the cost saving will come. Actually, that's why you have found that in terms of the cost of the material, it was higher. The EPS was higher than the conventional blocks. But now he's saying you should always, when you want to do an effective comparison, you should have compared the labor. You have factored in the labor, because that's where the cost saving might come in.
okay.
Yeah, we didn't. We'll do that.
Then there is a question. Can you see the question by Engineer Kyoko on the chart?
Yes, we do. We have the drawings. It's in the main document.
Okay. And then there is a question by Engineer Mutua.
Yes, in the documents, there is a section where we have placed the rates of the cost of materials, and we'll avoid using the no.
You do not just avoid no. You should give us facts. What has been done, what is remaining.
Yes.
All right. Any other question as I invite 5140?
Morning, my name is Catherine Njuguna.
And I'm Neil Kibat.
And our project is on structural and economic effects of using shredded plastic and rubber as aggregates in the production of hollow blocks. So in the global market, there are 300 million tons of plastic that are produced worldwide, and only 90% of this waste, and actually 90% of this waste is unrecycled. Alongside that, there is excess covering, which leads to environmental degradation to support the construction industry. All this is not in line with our SDG goals, which are to sustain, to promote sustainable development and terrestrial and marine preservation. Currently, in our country, in Kenya, in 2018, we had a housing deficit of 2 million housing units, and this number grows by 250,000 units every year. So we have a deficiency in housing, a pollution menace, and a degrading ecosystem. So how do we move from this to sustainable development and a clean environment? Hollow blocks could be plastic rubber hollow blocks could be a solution to this, because we are using the recycled materials which otherwise would pollute our environment, and also providing to come up with cheaper housing. Our main objective is to use shredded plastic and rubber in production of concrete hollow blocks for the use in rim slabs. Our specific objectives is to determine the material properties of shredded plastic and the rubber when used in the concrete mix for the hollow blocks, and also to determine the optimal concrete mix for the hollow block. Then we determined the effect of shredded plastic and rubber on the material properties of the concrete mix itself. And then afterwards, we evaluated the amount of material usage reduced in hollow blocks as an advantage of a conventional solid hollow blocks and control mass concrete hollow blocks. Normal hollow blocks use the concrete. Normal hollow blocks use stone and sand aggregate. So over the years, there have been other projects that have tested the use of plastic, glass, and rubber in the production of hollow blocks. So our project is conducting a full replacement of the aggregates with plastic and rubber. On our methodology, we were testing the specific constituent materials that is plastic, conducting effective analysis using specific gravity. Afterwards, we designed a concrete mix with varying proportions of the aggregates, that is, for example, 70% rubber and 30% plastic, 60% rubber and 40% plastic, then having a 50-50 mix, and the reverse with having like 30% plastic and 30% rubber. And then we had tests on concrete. On the concrete itself, the slump test, the compressive strength test, and flexural test in line with the standards. And then we had tests on the hollow blocks after we achieved the optimal mix. So we conducted the mixture absorption and compressive strength on the hollow blocks itself. And afterwards, we designed a ribbed slab containing the rubber infused plastic hollow block and also the control hollow block.
Okay, once we obtained our materials from the industrial area, we conducted a sieve analysis and specific gravity of the various particles, rubber particles, and plastic particles, so that we can understand the aggregation. So the rubber aggregate showed a representation of finer aggregates, whereas the plastic aggregate showed a larger representation of coarser or larger sized particles, and the maximum sieve size was 10 millimeters. The specific gravity of rubber was 1.15, and that of plastic aggregate was 1.08. So the slump also showed variation with increase in proportions of plastic. So the more workable mix was the one that had a higher plastic percentage, as you can see, 30% of rubber and 70% of plastic. And the least workable mix was that had the highest proportion of rubber content and the least amount of plastic. So we did mix design and varied the proportions, the ratios of rubber to plastic, and the highest compressive strength was obtained with the mix that had 30% of rubber and 70% of plastic. And also the 40-60% rubber to plastic ratio met the threshold provided by the Kenya Standard Case 02-625/1983, which sets a minimum of 2.8 newtons per millimeter squared for non-load bearing blocks. So once we did the compressive strength test, we went ahead also and do flexural strength test. So we inserted the flexural beam in this apparatus shown in the slide, and it was subjected to 3-point bending method. And also the flexural strength test showed with an increase in the percentage of plastic, the flexural strength also increases. And then the control experiment also had the highest flexural strength. That is, the control had normal aggregates, that's sand, and normal aggregates stone with 10 millimeters, the maximum aggregate size. So with the optimum mix, that is 70% of plastic and 30% of rubber, we went ahead and prepared concrete hollow blocks and checked for their compressive strength, which gave a value of 3.3 Newton per millimeter squared and a moisture absorption of between 1 to 2%. And when they failed in compression, they exhibited shear cracks, as you can see here and here in this diagram on the slide. So based on the unit weight of the hollow blocks, we did a comparison of concrete hollow blocks and the plastic rubber hollow block. So the plastic rubber one weighed 16.5 kilograms and the concrete hollow block weighed 24.7 kilograms. And the cost of the materials, when we evaluated the cost of each constituent material, we got 164 shillings for the plastic rubber and 155 for the concrete hollow block. So based on the unit weight, again, we did a design of a rib slab containing rubber plastic hollow block, and we obtained according to the area of steel required for the design of the rib slab, we found a difference to be at T10 on the rubber plastic hollow block and at T12 on the concrete hollow block. So the difference is that there are 2 T10s here at the bottom and 1 T12 and 1 T10 at the bottom of the concrete hollow block slab. So there's a saving on the material usage when you use a plastic rubber hollow block, which is lighter in weight compared to that.
1 minute remaining.
So as I conclude, we found out that the shredded plastic performed as a coarse aggregate since it had relatively larger particles compared to that of rubber, which had relatively finer particles. And the optimal mix for the rubber plastic combination was that had a ratio of 3 to 7 or 30% rubber and 70% plastic. And the strength, the major strength was being sourced from plastic and the cement as exhibited from the results, and 20% of material saving was witnessed as shown in the area of steel required and the steel provided in the slab design. So we recommend that in future studies, concrete class can be varied and production techniques also can be varied. That is the extent of vibration when preparing the hollow blocks, and a weight and cost reduction analysis of an entire structure based on the unit weight of the rubber plastic hollow block. Thank you very much.
All right, thank you. You have gone over about 8 minutes and almost 9 minutes. All right, now I welcome questions from the members.
Okay, I have a question. In the sieve analysis, you've shown us the gradation curves.
Yes.
Did you check whether they are falling within the limits required? Yeah, this one.
No, we did not. This is because the grading is directly related to how the plastic material was prepared and also the rubber material was prepared. You can each batch has a different curve because it depends on how they were shredded and the millimeter size of which.
So what was the essence of grading?
The essence was to for the design, for mixed design, to know how we can get a specific class of concrete. It was used in the concrete mix design.
Okay, though you should find out and try to understand why the grading and why it should fall within the curve. Thank you.
You can see, sorry, I have muted you. You can see the same comment from Engineer Kyoko. Include the upper and the lower limit in the sieve analysis graphs. Yeah, so that you can tell us whether it's falling the grading. I don't want to comment. This is so please observe the comment by Engineer Kyoko and Engineer Mandela. Okay, any other question? Okay, thank you for your presentation. Let's go to...
Our project was on the effect of the combined use of uncrushed river pebbles and crushed coarse aggregates on the properties of concrete. The project was conducted by myself, Benedict Omurwa, and my partner, Masi Mwendwa, and our supervisor is Dr. Gadhimba. On to the next slide. crushed aggregates are the most common form of aggregates because they're preferred because of their high strength, but the continued use of the crushed aggregates results in land degradation, as you can see in the photo attached. And therefore, there is need to, with the growing population, there is need to ensure maximum utilization of available resources. This can be done by the use of river pebbles as a construction material and not as simply decorative element. Problem statement and justification. Crushed aggregates, they present the advantage of higher strength because of their high bond strength, but they present the disadvantage of requiring more pace because they have higher volts and they have poor workability. On the other hand, the river pebbles, because of their smooth texture and their rounded shape, they present high workability, therefore have high workability, but the disadvantage is interlocking. The disadvantage is they present poor interlocking, weak bond strength, resulting in low strength. So an optimal combination of both will result in a mix with high strengths and requiring less work. Onto our objectives. The main objective was, as per our topic, to investigate the effect of the combined use of uncrushed river pebbles and crushed coarse aggregates on the properties of concrete. The specific objectives, the first one was to compare the physical and mechanical properties of both the uncrushed river pebbles and the crushed coarse aggregates. The second one was to determine the properties of fresh and hardened concrete made from the combined use of the two aggregates. And the third one was to determine the correct mix design and establish the optimal mix from the aggregates, from the pebbles and the crushed coarse aggregates. The scope, after collecting our materials, we did the comparison of the material properties of the materials, and then we did concrete testing on both the fresh and hardened concrete. And then after determining the optimal mix, we casted a beam from the optimal mix. The pebbles used are as per the slide, the yellow pebbles and the black pebbles. The limitations of the project, we only had one concrete class. We measured on the material characteristics and there was less focus on the structural behavior of the uncrushed river pebbles. On the literature review, previous studies were conducted on the use of the combined use of various aggregates, but the major focus was on gravel, and we aimed to focus on the use of pebbles in construction, especially in Kenya.
Our methodology from our main object, from our objective, we determined the properties of coarse aggregates. Then we determined the properties of both fresh and hard concrete, and from the optimal mix, after the mixing, we used to determine the fracture strength by casting the beam. From the sieve analysis of the sand was within the envelope, and it was good to produce a quarried concrete. From objective 1, the sieve analysis of the aggregates, that is coarse aggregate, crushed coarse aggregate and uncrushed river pebbles, the particle distribution was good and they fall within the envelope. From objective 1, that is the same, the properties, the ACV, for the black pebbles, it has high ACV, meaning it has less impact to resist, less crashing resistance. And for AIV, uncrushed black pebbles and AIV, meaning it had less impact on resistance. The crushed aggregates, that is the coarse aggregate, they were more freaky from our resort, and black pebbles were less freaky, followed with the yellow pebbles. For our workability, the mix with higher amount of the river pebbles, that is black, which was more smoother and high packability and a high slump, for as the quantity of the pebbles were reducing, the slump was reducing. For the failure mode, that is from objective number 2, of the properties of the both hand and fresh concrete, the mode of failure was that after the center point rounding, that it was they crushed the crushing was explosive and columnar, that is, it was satisfactory. And from the mix, that is the optimal mix that we casted the beam, the fractional test, the mix that was the control was the crack was wider, and for the 25% that and the maximum strength, the crack was less wider, meaning that they can still be incorporated in structural elements. Compressive strength, the compressive strength was for the black pebbles was reducing from the control under a compressive strength of 31. And if you look at the 25% river pebbles, it had the maximum compressive strength, and that's what we used for casting the beam from our objective. That is number 3. We casted the beam using the optimal mix.
Conclusions and recommendation. From our first objective, we were comparing the properties. So we found that the material with the greatest resistance to crushing was the uncrushed black pebbles. With the greatest resistance to impact was the uncrushed yellow pebbles. Highest specific gravity, uncrushed black pebbles, and the most flaky was the crushed coarse aggregates. On to the second objective, the material, the combination with the highest cube compressive strength was the control, closely followed by our optimal mix, which was the 25% uncrushed black pebbles. The most workable mix, with the one with the highest slump, was the 75% black pebbles, and the mix with the highest flexural strength was the optimal mix. The recommendations: we will recommend the use of uncrushed river pebbles as a partial replacement crushed coarse aggregates in construction, and further research will be done using crushed river pebbles instead of uncrushed. Thank you.
All right, thank you for your presentation and keeping time. So question from the panel members?
My name is Batilda, and my partner. We're going to present on the study of stabilized adobe blocks prepared using baggase fiber and corn cob ash as partial replacement for cement. Our backup solution: adobe blocks have low durability and pure resistance to water, and hence the need to improve the block. Our problem statement is due to the adobe blocks have been used previously for construction of temporary structures due to the low compressive strength and their capacity and their resistance to them. So we are trying to improve the adobe blocks so that we may be able to construct permanent buildings since the cost of construction is lower and it leads to provide shelter for the growing population in general. Our overall objective is to improve the potential of stabilized composite art blocks as a sustainable construction material for eco-housing, and for our specific objective to determine the physical properties of red coffee soil, investigate baggase fiber in cutting of blocks made with red coffee soil, and also to investigate the effect of corn cob ash and cement on the mechanical properties of adobe blocks, which will result in the investigation of the load carrying capacity of composite walls made of evolved eco blocks. Our research gap is that there has never been any study on the corn cob ash used together with baggase fiber as a soil stabilizer. And that's why we're investigating the effect of a corn cob ash and baggase fiber on the compressive strength working on compressed hard blocks. Our methodology: the materials required the soil, baggase fiber, corn cob ash, and cement. The soil test was moisture content determination, Atterberg limit and seed analysis. Our block test was which are according to BS, and on to our results.
We get the results. There's a composition of the block mixture that we use for block production. Sorry. On to the results. We are supposed to fulfill our objectives as stated above, and for the first objective, which was to determine the physical properties of the red coffee soil, the particle distribution, the sieve analysis which we did, we chose the white sieving, and this was to classify the soil which we later classified as clay as it contains 88.9% of the content. The next table shows the other physical properties of the red coffee soil summarized in one table, which gives the moisture content, liquid limit, plastic index, which I'll comment on later, the linkage, the linear shrinkage, and the dry density, as well as the optimal moisture content. So on objective number 2, we move to the linear shrinkage, whereby we selected blocks which we had made from the compositions I was shown you earlier. And as you can see, the number of cracks and the linear shrinkage, and I can comment on that, whereby as we introduced or added the corn ash and baggase, the number of cracks reduced as well as the linear shrinkage. Else we observed that there was no crack on cement, on addition of cement. And to our next objective, which was objective number 3, we were to test on the blocks and determine the compressive strength. In this sector, we had 2 variables, which was cement and corn ash as the main materials, which are supposed to vary. The table shows the red soil compressive strength without any addition of any stabilizer, as well as with cement in different proportions, 5% and 10%. And there's a graph which is supposed to show the compressive strengths of the different compositions of blocks we made. And there's a table which shows the same. I can comment on this and discuss that red coffee soil by itself provided after 28 days a compressive strength of 2.84, which is higher than the KS standards of 2.5 megapascals, can be used for construction of compressed earth blocks. However, it failed in water absorption, and that's why we were supposed to add stabilizers to bring it there. So on the water absorption test, which was carried out, as you can see, the red coffee soil unstabilized failed before 4 hours. The rest, only blocks which we added cement were able to sustain after 24 hours, and that's how we were able to find the water absorption capacity of the block. Let's go to objective number 4, where we were supposed to test the on a wall panel. And here we constructed 3 walls. One was with unstabilized block, the other was with stone block from Darugo, and the other one was stabilized red soil block. As you can see, there's a graph which shows the displacement of applied load, and from this you can discuss and say that the wall panels from the stabilized block had a higher loading capacity as compared to the masonry blocks. There's a there's stress and strain characteristics of the top panel, also bid for the bottom panel. Finally, we did a cost comparison between the blocks we made, which was one, which is the RC, which had the highest compressive strength, and compared it to the conventional block, which was the stone block from Darugo. As you see, the cost for construction for making of the brick was lower, with 2,026 per meter squared of the wall, while the conventional came at 3,000.
To our conclusions, the different stabilizers used had an improved structural properties on the earth blocks. The addition of cement, corn ash, and baggase fiber on the red soil, they reduced the number of cracks and the amount of shrinkage. The addition of 5% of corn ash to the red soil improved the compressive strength of the block from 2.8 to 2.9 megapascals, and with a further addition of 5% and 10% of cement, it increased to up to 3.95 megapascals. The compressive strength of the stabilized earth block was higher than that compared from the block walls from the Darugo. Our recommendation, so as to optimize on the performance of composite blocks, further studies should be carried out so as to determine the exact percentage of corn ash and cement that are needed to stabilize the red coffee soil, so as to achieve 2.5 megapascals.
Okay, all right. Thank you for your presentation. Now the floor is open to questions. Panel members, let's get your views on this presentation. Engineer Madera, you are around? Engineer Kioko, Engineer Mtua, Engineer Juki?
I'm around, but I'm okay with them.
Okay. Also, Engineer Madera is okay? All right. Okay, I think it's okay. Thank you for your presentation.
Good afternoon all. This is Moses and Bernard Kabucho. We are presenting on the topic of effects of incorporating wheat straw on the properties of concrete. On the content, we have introduction, problem statement, objectives, scope, limitation. We will go to literature review, methodology, results, and discussion. Then we'll summarize with conclusions and recommendations. Now to the background of the study. Concrete is the most widely used material in construction, in the construction industry. And a research which was published in 2019 by a journal by the New York Times said that concrete production leads to production of about 10% of the carbon. Therefore, if we adopt a green building technology, we shall help minimize this production of carbon footprint, and also use this material in the production so as to improve on the structural design. For the problem statement and justification, wheat straw, which is an agricultural byproduct, for most, it is being disposed through burning and dumping. The dumping causes landfill as organic solid waste, and through burning, it causes air pollution, as you can see on the photo on the right. So in order to minimize this, it can be incorporated in concrete, and it can also, according to the studies previously done, it also shows that it can improve on the tensile strength of concrete and the flexural strength of concrete. Now to objectives, the main objective is to the effect of using wheat straw as a material in concrete production. And to the specific objectives, we want to see the suitability of wheat straw. How shall we achieve it? First, we shall determine the effect of wheat straw content on the workability of fresh concrete. And then we shall determine the physical and mechanical properties of wheat reinforced concrete. This is now where we test for the compressive strength, the flexural strength, and the split tensile strength. And finally, we need to see what is the optimum quantity of this straw, which, when incorporated for reinforcement in concrete, helps to achieve the best results. For the scope of the study involved the experimental design and lab tests, which were done at the Jkuat materials lab. Then thereafter, we received the lab under limitation of the 5 for the test, and we had the inability to quantify the reduction in the carbon footprint of the social limitation, then lack of perform the durability test. And now to the literature review, this table shows us some of the on vegetable fiber. For example, sisal fiber has been incorporated in concrete. We have rice husk, we have banana fiber, we have jute fiber, we also have hemp fiber. There are other fibers also, vegetable fibers, which have been incorporated in reinforcement of concrete. But then little has been done on research. There have been research have been done on the application of rice husk, where fiber, sisal fiber, and other types of fiber, and also a little has been done on wheat straw, and even on the application. When we look at the rice husk, it has been applied in terms of fiber and other forms such as the ash. But when you look at wheat straw, the material itself, it's least applied in the concrete making. For the methodology, we did a material collection where we collected finer concrete, the wheat straw fiber itself, and the coarse aggregate, where we did the preliminary test on the coarse aggregate, on the river sand and the coarse aggregate. We did sieve analysis first, then we went to main tests, which were done on both plain and reinforced concrete. On the fresh concrete, we did a stamp test, and then on the hardened concrete, we did tensile, compressive, and beam flexure test. Now to the results and analysis, we can see from this graph on workability that the workability was observed to increase compared to that of the control. The control had a workability of 11 millimeters, and as we continued dosing the quantity of it go up to 2.5%, we see that the workability increased. Now to the compressive factor, it was observed that there was a decline in the compressive strength as tested on 28 days, 14, and finally 7 days. This decrease is attributed to the increase in water content, water content. Thus, it disrupted or interfered with the matrix of the concrete mix. Thus, workability was observed to increase and compressive strength was observed to decrease. The next result was on split tensile strength, where there was an increase as we continued to increase the percentage basis of wheat straw in the concrete matrix. There was an increase from plain concrete to 0.5% dosage. Then there was a decline. Then there was an increase from 1% dosage to 2.5%. This can be attributed to the increase in the body strength, or that is attributed by the addition of wheat straw dosage, but it goes up to an optimum until 0.5, after which there is no significant bonding effect of wheat straw on the concrete matrix. Now, at the flexural strength, you can see that the flexural strength increased with a continued dosage of wheat straw from 0.5% to 2.5%. But now, the increase was observed at wheat straw dosage of 0.5% of the wet mass of the concrete mix. This is because of the improved bonding in the concrete mix due to addition of wheat straw, which acted as fiber to improve on the flexural strength. In the conclusion, we had workability increased from 11 millimeters at 0.5 to 16 millimeters at 2.5 dosage. Tensile and flexural strength increased with the optimum of 2.17 MPa at 0.5, and also the flexure of 4.1 MPa, 0.5 dosage. The compressive strength of concrete reduced by 1.202 MPa at the optimum percentage. The optimum quality of wheat straw required for suitable strength of concrete was established at 0.5%. Now to the recommendations, we had a limitation. From the limitations, we see that we were not able to study on the cracking behavior due to incorporation of wheat straw. Therefore, we recommend that future researchers look more time so that they can observe this cracking behavior, and also the durability. Concrete, the timeline we had was limited. Therefore, we were not able to perform the durability effect of use of a wheat straw fiber on the properties of concrete. We are also limited to class 25 concrete only, and therefore research will be done on the usage of this wheat straw on other concrete mixes, other classes of concrete, so that we can come up with a better analysis of this straw fiber on the material, the properties of concrete. Thank you all for listening.
All right, okay, thank you. You have spent 9 minutes. That's a lengthy presentation. Question from the panel members? Okay, thank you for your presentation. You can leave.
Hey there. Subscribe to my channel. And also press this bell icon.